Hi, welcome back to our lecture. Today we'll talk about Lecture 3. Lecture 3 you'll be introduced to a new concept in signal and systems, which is the convolution. This is today's lecture outline. First, you'll be introduced to definitions of convolutions on what convolution actually is. And then we'll move to evaluate convolutions of signals or systems, where we have two things. One is the discrete time convolutions, another one is a continuous time convolutions. So there are some mathematics involved in these two steps. And then finally, we'll move to see properties of convolution. There are several properties that you should remember. Now let's look at the module learning outcome for today's lecture. It will still be LO1, which is to evaluate signals and systems to understand their properties. So this will be the last lectures to evaluate on LO1. Before we go into the concepts of convolutions, let us revise back a few signals that you have learned in the previous lecture. The first is the unit impulse signals. Unit impulse signals has just a spike with the area of 1 at beginnings at n equals to 0 if this is only n. If let's say this is n minus 1, then it will be n equals to 1, whereas n plus 1, there will be n equals to minus 1 over here. While the rest of the signals on different timestamp will be all on zeros, as shown in the graph on the right here. Whereas for unit step signals is defined as a step that started off at time equals to 0. So any time below 0, it will be all 0. As time reaches 0, these signals will step up to 1. And then any times beyond the time signals of 1, it will be all 1 here. So this is a discrete signal, so therefore you will see a lot of spike of 1 instead of just a single 1, like a normal step signal here. So if you look at the discrete unit step signals, which is shown over here, you'll see that they actually consist of many spikes at n equals to 0, n equals to 1, n equals to 2, so on and so forth. So you can actually decompose these signals into many unit impulse signals. So we have the first unit impulse signals at n equals to 0, which is over here. And then we have the second unit impulse signal, n equals to minus 1, so on and so forth, all the way until n equals to infinity. Therefore, we have this expression here. A unit step signals is equals to summations of each of the impulse signals from n equals to 0 all the way to n equals to infinity, which you can see from this figure over here. Okay, next, let us look at any signal. So let's say we have a signal xn, and this signal xn can be any random signals as shown in these figures over here. And if you want to decompose this signal xn into many different impulses, we can also do it. So let us look at examples of when n equals to 0. So when n equals to 0, we can decompose it into just a single impulse signals when n equals to 0 multiplied by the magnitudes of the signals when the signals is at time t equals to 0. So in overall, you will get these expressions out, which is the x at time t equals to 0 multiplied by an impulse signals at n equals to 0, or n equals to 0 here. And so on for all other signals. Let's say for the second signal over here, we can also define the same thing. And now we have one impulse at n equals to positive 1. So it's delta n minus 1 over here, and multiply by a signals, the random signals that we are evaluating now at time n equals to 1 as well. So if you write out the summations of all the signals on the left and on the right, we are coming to these particular formulas, and we have the formulas which is these particular signals at certain time multiplied by the impulse response, or multiplied by the impulse signals of that n equals to that time. And that time will start from negative infinities all the way to the infinities. So it depends on how long your signal is on the left side and how long your signal is on the right side. Alright, next let us look at systems. So if you look at these systems over here, the system, we call it system T. Sometimes we wonder, how are we going to call this system, or how are we going to define these systems? Any mathematical representations that we can refer these systems to? So someone thought of a way where we can inject an impulse signals to the input of the systems, and then we use our oscilloscopes to measure the output of the systems. And then the measured output, which is, let's say, is Hn. This is a discrete time signals again. And this Hn is so-called a response to a unit impulse. And therefore, it is called an impulse response of these systems. So now we can define these systems as a system that has the impulse response of H to N. So now you must be wondering, why are we even care of having an impulse response for a system, let's say system T? So for impulse response, we input with the delta n, and then we find out what is the response of the systems, and then we represent these systems as Hn, the impulse response. So why are we even doing that? So let us look at any signals. Just now you have learned that any signals can be decomposed into this form. It is a summation of a constant, which is the signals at different time stamp, with impulses at different time stamp as well. So now if we substitute these signals instead of the impulse signals to our systems, and so what do we get as the output? So remember that our systems is basically a functions. At any inputs, it will be transformed by our systems to produce the. In this case, the yn is the transformations of xn, and the xn over here is our random signals, or any signals that can be represented by some constants multiplied by a train of impulses. And therefore, if we substitute this xn as our mathematical formulas over here, it is a transformations of these whole lumps of impulses. And as you know, we are studying linear time invariant systems. So one properties of linear time invariant system is that we have the associations and the superpositions principles. So the summations of all the constants multiplied by the signals will be just the summations of the constants multiplied by the transformations of the signals. This is the properties of linear time invariant systems. And therefore, if you look at this one, transformations of impulses, as you learned in the previous slide, transformation of impulses is just equals to our Hn, which is our impulse response. And finally, we can write our formulas as the outputs of the systems is a summation of the inputs of the systems at certain time k multiplied by the impulse response of the systems at that particular time k. So n minus k over here. So that is where impulse response become very important, because once we get the impulse response of the systems, we are able to find out the outputs of the systems given any inputs to it by applying this formula. Alright, so now you look at these formulas is the signal, the input signals at time k multiplied by the impulse signals at time, the impulse response, not just the impulse signal, the impulse response of the system at time n equals to k, and k will span from negative infinity all the way to infinity. And so these particular signals, or these particular formulas, it looks quite complicated. It still looks quite complicated because you need to have multiplications of a constants with the impulse signals from negative infinity all the way to infinities. So we can call it a convolutions operations where we just write it in a simple way, just write it as xn convolutes with hn in this case. So now you have to remember, whenever you see the convolution symbols, this is not a multiplication, this is a convolution symbols, you have to associate it with these formulas. Xn convolute with Hn will be the summations from negative infinity all the way to infinities of this xk multiplied by the impulse response at that particular k. So k is from negative infinity to positive infinity. So now every time when we look at a system, we represent the systems with its impulse response. Let's say this system impulse response is given to you, Hn. And then now you have an input xn, and if I ask you what is the output of the systems, you can just tell me the output of the systems is the input signals convolutes with the impulse response of the systems. So you can just simply write it as the output is the convolutions between the inputs and the impulse response of the systems. Alright, now let us look at these examples. So in these examples, we are saying that we have a signals, which is indicated here, that will pass through a systems which has an impulse response as indicated over the graph over here. And so what is the outputs of the systems? And now you know the outputs of the system will be the input of the systems, which is in this case xn, convolute with the impulse response of the system, in this case is the hn. And now let us look at these two signals and systems. For the first signals, the input signals, we can write it in this form as well, 0, 1, 2, 1. So this 0 corresponds to when time n equals to 0, we have a zeros over here. And then therefore sometimes we put an arrow to indicate that this is the timestamp of 0. And then this 1, the 1 over here, corresponds to the magnitudes of the signals at timestamp equals to 1. The 2 over here corresponds to the magnitude of the signal at timestamp equals to 2. And the 1 here corresponds to the magnitude of the signals at timestamp equals to 3. And therefore we write it in this particular form. This is just additional information for you. So again, for the systems, we can also write it in this form. So in this case is 1, 1, 2, and 2. And the arrow should be on this 2 here. So we know that this particular 2 is at time t or time m equals to 0. And this n equals to 1. This n minus 1, n minus 2. And now back to our questions. When the signals is passing through these systems, what we can do is that we can write down the formulas that you've seen earlier, the convolution formulas, the xn convolute with hn. And now we need to identify how many k's are there. So what numbers that k spans from? In this case, you look at the signal xn. Xn has only 3 cases. Only 3 times and 1, 2, and 3. So the k will be just k equals to 1 in this case, k equals to 2 in this case, and k equals to 3. And all other k's will be 0. So we are left with just 3 different terms. Now for each of the terms, you need to write down n minus k here. So it becomes hn minus 1, hn minus 2, and hn minus 3. For the next steps, we are going to calculate in each individual n over here. So the calculations results are shown at the bottom. If you substitute n equals to minus 2, so everything you substitute minus 2 here, minus 2, minus 2, minus 2, you get the answer as 0 because every terms over here are 0. So there's nothing we can see in minus 2. So let us look at minus 1, when n equals to minus 1. So when you substitute minus 1 on the three places, on these three places, minus 1, and minus 1, you will obtain x1 multiplied by h minus 2 plus x2 multiplied by h minus 3 plus x3 multiplied by h minus 4. And if you look at your initial system's impulse response, h minus 2 is at this point equals to 1. H minus 3 is equal to 0 because there's nothing on minus 3. H minus 4 is also equal to 0 because there's nothing on minus 4. So in this case, x1 is 1 and h minus 2 is also 1. The rest are 0 because anything multiplied by 0 will be 0. So therefore your answer will be 1. And then you do the same things for n equals to 0, n equals to 1, all the way until you reach a place where you get everything as 0 again. So let's say this is 0, and this is 0. Then you can stop. So you start from everything 0, and then you have to work all the way until everything's to be 0 again. And then that is where your limits are. So finally, you obtain the results. When n equals to minus 1, which is this case, you get magnitude of 1. So therefore you write it here. When n equals to 0, you get 3, you get 5, you get 7, you get 6, you get 2, and from 5 onwards is all 0 again. So there's nothing from 5 onwards. Alright, next one, let us look at the method 2. Method 2 is a method of using graphical methods. So there are a lot of steps that you need to follow, which are listed over here. Just take a look at all these steps, and in the next slide onwards, we'll use an example to execute each of these steps. That will be easier for you to remember. So now, let us take the same examples again. And these examples, you have know that this is, the xn is at 0, 1, 2, 1, while the yn, the hn is at 1, 1, 2, 2. So for the first steps in method 2, or the graphical methods, you need to reflect your hk to become h minus k. So how do you do that? In order to do that, you just reflect all your hns on the axis of 0. So whatever on the right side, you just put it on the left side, and whatever on the left side, you just put it on the right side. And so you arrive with this answer. So at 0 is still at number 2, and negative 1 is now magnitude of 2, which is the same as here. At 1 and 2 is of magnitude of 1, which is correspond to negative 1 and negative 2 over here. And now the second step is to move this particular h minus k and superimpose it together with xk on the same graph. So in this step, it is very important that you need to make sure the zeros remains the same. So look at this. The blue color lines here are the h minus k, and the black color lines are the xk. So you are putting both of them on the same axis in this case. On the third step, you are going to shift your h minus k to either the left or to the right, so that the first, the rightmost instance of your hk, the blue color dots if you can see here, will superimpose with the leftmost instance of your xk, which is the black dots over here. So in our case, we are going to shift it to the left side. If you still remember previously on our graph, it looks like this, where this is the xk, this is the xk, and let me change the color of the pen. So let's say we have the blue color also, and our h minus k was here. 1, 2, 3, and 4, and this is the zero position. And now because there are two of them superimpose each other, so we need to shift the graph to the left so that this superimpose will go to the left side. So there will be only one superimpose as shown over here on this graph. So once you shift it to the left, you have to remember, whenever you shift to the left, let's say you shift to the left for one step, you will start at n equals to minus 1. N equals to minus 1 because you shift it to the left for one step. And now you can start doing your calculations. So the first calculations is to find out you multiply off the superimposed magnitudes, and then you sum up the result as your y. So in this case, there's only one superimposed, and both magnitudes are 1. So you end up with 1 multiplied by 1. This 1 comes from the xk. This 1 comes from the y minus k. And your result is 1. For the next steps, you will need to shift your h minus k one step to the right. So this is fixed. You have to step it one step to the right, and then you apply the same principles where you multiply all the superimposed instances, and then you add them together. So in this case is 1 multiplied by 1 because both are 1, and this case is 1 multiplied by 2, and then you add them together, therefore you get a final answer of 3. And just now remember, at the previous step you have y minus 1 equals to 1, and therefore now this become y0, and then so on and so forth. We are going to find out what is y1, y2, and so on our next slide. And so we need to repeat the process of shifting 1 to the right every turn, and then again to find out what is the summations of the multiplications of each of the superimposed impulses. So let's look at one more example. So in this case, where you slide to one side to the right, you will get 3 superimposed instances. This is 2 multiplied by 1, and this also 2 multiplied by 1, and this is 1 multiplied by 1 itself. So therefore you get this answer as 5. And then when you shift it further to the right, another one steps, you use the same method, you'll find out the answer to be 7. And then again shift it to the right again, and then you'll find out the answer to be 6. And finally you shift it to the right and find out the answer to be 2. And then you continue shifting to the right, and you notice that once you shift to the right, the blue color graph will be shifted to the right, and there is no more superimposed after this step. So it tells us that anything beyond n equals to 5 or above, it will all be 0. And then finally, you can arrive with the final answers. The first answers here is just y n equals to minus 1. So you got 1 just now when you do the calculations. And this is yn, y0, and you get 3. And this y1, y2, y3, y4, and as I said earlier, y5 and above are all 0. So we need not to even show them. So these answers will be the same as the answers that you have found in the method 1 as well. Next, let us look at the third method to solve the convolutions between a signal and a systems. And this is yet another method to do the same process, but in my opinion, this is one of the easiest methods to do. And to start with this method, we look at our signals and also our systems. So again, like the other two methods, you need to at least include the zeros here. And for the third method, what you're going to do is that you just write down the magnitudes of your signals over here. So 0, 1, 0, 1, 2, 1 and correspond to 0, 1, 2, 1 over here. And then for your systems, the impulse response Hn, you write it on the other axis. So let us write it over here. 1, 1, 2, and 2. And then this is actually a tables that you are going to use later. So what we are going to do now is to multiply both the numbers over here. So these columns here is zeros, and then the rows here is 1. So 0 multiplied by 1 is 0, and then 0 multiplied by 1 is another 0. So wherever at bottom of the 0 will all be 0. And 1 multiplied by 1 will get you 1. 1 and 1 multiplied by 2 get you 2, and 1 multiplied by 2 get you 2. So for the 2 is 2 times 1 is 2, 2 times 1 is 2, 2 times 2 is 4, and 2 times 2 is 4. And finally, 1 times 1 is 1, 1, and 2, 2 here. And then next up, you will need to draw a diagonal line, not just a diagonal, you need to draw multiple of diagonal lines to class each of the numbers. So the diagonal line have to draw it this way. So the fourth line will have fourth number, and then it will decrease again, go back to this. And once you have drawn the diagonal line, what you need to do is to write out the summations of each of the diagonal columns. So the first summations at this point is 0. Alright, so this is the point that we are looking at now. And at this point is 1 plus 0, so is 1. At this point is 2 plus 1 plus 0, so it becomes 3. And then the next one is 2, 2, 1, so it's 5. And then the next one 2, 4, 1, so it's 7. And then followed by 6, and finally by 2. Alright, now you have a series of numbers, and then you need to determine which number is at 0, which number is at the origin, n equals to 0. So in order to determine that, you need to find out the zeros on both sides. So for our signal xn, the 0 is over here, and for our signal or our system Hn, the 0 is over here. So if you look at the row, the columns, the first column and the third rows, the zeros lies on this particular place here. So this one corresponds to the 3, so we can conclude that the 0 is actually at 3. So if you want to draw out the finals graph, let's say this is 0, this is magnitude of 3, and this is magnitude of 1 at -1, and then this is magnitude of 5, magnitude of 7, magnitude of 6, and magnitude of 2. So we just write the corresponding timestamp over here. So this is n. So this is our final answers, which is exactly the same as the answers that you've seen by using method 1 and method 2. But I found that using this method is a much more straightforward and easier methods to do. However, this method will only work on discrete signals and systems. So all your timestamp must be discrete. It cannot be continuous. Once you have a continuous systems or signals, it will not work for this method. Alright, now for these examples, you have a signals given to you with xn, which is 1, 2, 1, 2, starting from 0. And then you have your impulse response of the systems given to you, which is just 1, 1, again starting from 0. And you are required to find out the output, which is the convolutions between the inputs and also the systems. And you can use any methods that you have learned, the 3 methods, but in my opinion, the third methods will be the easiest for discrete systems. So now let us try with the third method. So in order to draw the tables, we just write down what is xn over this axis, 1, 2, 1, 2, and we write out what is hn over the other axis, 1, 1, and make sure the 0 axis, the zeros are included. These 2 zeros are included. So now if you draw it properly, 1 times 1 is 1, 1 times 1 is 1, 2 times 1, this will be just 2, 2, this will be just 1, 1, and this will be just 2, 2. And then you need to draw a diagonal line. Draw a diagonal line this way. Okay, so this was the line earlier. Alright, now the answer will be 1, and then this is 2 plus 1, so it's 3, and then it's 1 plus 2, so it's 3, 2 plus 1, so it's 3, and finally 2. And where is the origin? The origin is at where both origin intersect. So in this case, this was the origin, and this was the origin. So this will be the origins for your new signals. So finally, the answers in terms of graph will look like this graph over here. At times n equals to 0 is 1, then followed by 3, 3, 3, and then followed by a 2. And then all the rest of the values are 0. All the examples that we have seen in the previous graph are all on discrete time systems. So what if the convolutions in continuous time systems? So let's say we have a signals that go into a systems, and then we want to find out what is the output, and this system happens to be continuous. We have ht and xt over here, and both of them are continuous signals and continuous systems. So if you remember the formulas for discrete time systems, we have yn equals to summations of k negative infinity to positive infinity xk with h n minus k. So for continuous systems, the formula basically stood the same. So you just copy back wherever it is, x tau, ht minus tau, and instead of doing summations from k equals to negative infinity to positive infinity, now you do an integration of these signals multiplied by the impulse response, which is the systems, over d tau from negative infinity to positive infinity. So this is the formula that you can apply to solve convolutions between continuous signal and systems. Now let us look at one example of the convolutions of continuous system and signal. So we have our systems indicated by h tau, which is just a step systems, and then we have our signals, which is negative exponential signals represented by x tau. So the first step, you look at the formulas that you are going to apply. You are actually needed to reflect your h tau signals and then move it t steps, either to the left or to the right, depends on the sign of the t. So you learn this in the first 2 lectures in this course. So the first step, you are going to reflect these signals, and it changed to this, the third graph over here. And then you need to move it towards t steps. And in our first case, we are analyzing when t smaller than 0, so it's moving towards the left side. Now what you need to do to satisfy this formula is you need to multiply both of them, because you look at this is x tau multiplied by h t minus tau. And after you multiply them, you will need to do the integration. So first you do a multiplication, and you notice that for these two graphs to multiply together, anything before zeros are all zeros for your signals, and anything after zeros is also zeros for your systems. And thus, by multiplying them both together, you get yt equals to 0. There's nothing you can compute at all. Integration of 0 is still 0. And next, you slowly shift the t towards the right. So your ht minus tau will be slowly shifted to the right. And you notice that once, in this case, when your t is greater than 0, meaning that any times after zeros, they are indeed overlappings of your system and your signals. So you can actually do multiplications of them. So the formulas to do multiplications is over here. You need to multiply your signals together with your systems, that is shifted and reflected. And if you look at this graph over here, the overlapping is only between 0 to t, and therefore your integrations can only work from 0 to t, because anything beyond t is 0, and anything before zeros are all 0 as well. And then to multiply both of them together, you notice that the magnitude of this graph is just 1. So it's basically 1 multiplied by the sickness, which is e to power of negative a tau in this case. And therefore you get the e to power of a tau over here. And to do these integrations, you're able to obtain an answer 1 over a multiplied by 1 minus e power to negative at. And notice that when t greater than 0, when this particular system moves further to the right, the whole answer will still be the same. It is still satisfied this 1 over a multiplied by 1 minus e power to negative at. And therefore, your final answers is this. Your yt is equals to basically the answers that you found earlier multiplied by a step sickness. Why do we write it as multiplied by a step sickness? It's because step sickness has a magnitude of 0 when everything's below 0 times 0, and has a magnitude of 1 for anything above times 0. And therefore it satisfies our criteria. When time t equals to smaller than 0 is 0. When time t is greater than 0 is equals to this particular answer here. So that is your final answer. Alright, next we try to use method 2, which is the graphical method, to do convolutions between the continuous signals. And for method 2 to be used in continuous signals, the continuous signals must be a square signals in order to work. Because if it's not a square signals, you will not be able to find out the areas and also the multiplications of them. So now let us try method 2. So if you still remember method 2, you will need to use your impulse response. In this case is write as wt, but you can see it as a ht, is the same. And this one you see as a xt, is the same. You need to do a reflection on the axis, and in our case here, the reflections will be exactly the same, because this is just a rectangular signals where it has the width on both positive tau 2 divided by 2 to negative tau 2 divided by 2 over here. So after you do the reflections, you need to move these signals all the way to the left and then place on the same axis, if you still remember. So you achieve this particular graph now. So after you do reflections, and then you move it all the way to the left and place at the same axis where the right of the h will touch the left of the x. So they will touch one another here. And in this case, you need to record now how much you have shifted to the left, which is here. So this one, we know that we have already shifted to the left of tau 1 divided by 2 plus tau 2 divided by 2. Because this is tau 1 divided by 2, and this one is a tau 2 divided by 2. You have shifted that much of amount to the left. And for our first case, when they just barely touch one another, there is no area at all. So you are finding out the intersection area in the continuous case. So there is no intersection of area at all. So therefore the answer is 0. So if you want to draw out the graph here, the output graph, at this particular time, this is tau 1 over 2 plus tau 2 over 2, and of course it's a negative number because it's on the left side. Anything before these particular lines are all 0. And it will only start increasing at this point, which we'll see in the next slide. So in this next slide, you are going to slide your systems towards the right. So let's say I draw out what it was just now here, and then you have your systems over here, which is slightly taller but slimmer. And now you are going to slide your systems towards the right side, meaning that the system will slowly eat into the second graph. And then while it is doing that, you are required to find out the area, this area, and multiply by the magnitude of the top parts here. And as this particular bar sliding more and more to the right, as you can see, the final result is here. As it slides all the way to the right, where its left edge intersect with the left edge of your system, your signals, this area multiplied by this constant will be the maximum. And therefore, we pause here for a while. And then you look at the answers on the right. It starts at this point where everything was 0. As it slides out, the area multiplied by the constants slowly increase. And it will reach its maximum point when it has slided through tau 2 amount of time. So therefore, you look at this. This is tau 2 amount of time. It will reach its maximum area, and this area is determined by this particular value is determined by the area multiplied by this constant, and the area is A1 times tau 2. This is the area because this is tau 2 and this is A1 multiplied by A2. So therefore you have A1, A2, tau 2 over here, and this is where the answer comes from. A1, A2, tau 2 at this point. And then this particular graph will need to continue slide to the right, and we'll explain it in the next slide. So at this stage, as our signals or our system sliding to the right, where always maintains within the square box over here, the area multiplied by the constant here does not change. From here, just now it slides to the right, everything remains the same. So that explains why our answers from this particular time instance are always the same. And it has slides for another tau 2, so in this case, it has slides for tau 1 divided by 2. It's not tau 1 divided by 2, but it's tau 1 minus tau 2 amounts of time. That is where this one comes from, tau 1 minus tau 2 amount of time that it has sliding through. And finally, we need to slide the bar from within the A1 to out of A1. So just now it was here. And then we need to slowly slide it out. And as it's sliding out, the area will slowly decrease. And therefore, the area multiplied by the constant A2 will be decreased in a linear way as well. So that is why you have seen this decreasing of the result. And at this point, which is when the WT has totally separated with the VT. And this point will be, again, is tau 1 divided by 2 plus tau 2 divided by 2, because this is where it is completely separated from A1 and between the area A1 and area A2. And therefore, anything after this line will always be 0, because no matter how much you slide to the right, there's no more area that is included by both the region. And this is finally your final result, where you can draw it out. It's like a trapezium. So this is the final answers for you to see more clearly. And next up, let us look at some properties of convolutions. So there are 3 basic properties. Later on, you will see a lot of these commutative, associative, and distributive properties for many other things that you'll learn in this module. But now stick to convolutions. It says that convolutions is commutative, meaning that if you have xn convolute with hn, it is the same as hn convolute with xn. What does it tell us? It means that, let's say if you have signals that pass through a system, this is xn and the system is hn, and the result is the same as you have the systems that pass through the signal xn. The result is the same. These two will be the same. This is the commutative law. So earlier on, when you do convolutions with one signal and one systems, you can actually do it the other way. So you can actually reflect signals instead of reflect systems, and then you do the graphical methods. Or in the method number 3, when you have the tables, you can actually write the systems on the left columns instead of on the top columns. So the second law is the associative law. It says that when xn convolutes with two different signals or systems convoluted together, it is same as it convolute with the first system first, then convolute with the second systems. So this is the associative law. So what it means is this. So when you have a signal xn, and then you convolute with one signal h1n, and this result will be xn h1n. And now if you pass this xn h1n into h2n, what is your result? Naturally, you just do convolution again. xn convolute h1n and convolute h2n. So which is this particular representations on the right. But now this associative law tells you that it is same as convolute both the system together first, then only you convolute through the xn. So what it tells us is this. Now this system become the same when you have a signal xn that go through a big system, and this big system is h1n convolute h2n. They are the same now. So you can do the convolutions of the system first, then only you convolute with your signal. And finally, look at the distributive law. It says that xn, your signals, convolutes with additions of your systems, two systems added together, is equivalent to convolutions of the signals with the first systems plus the convolutions of the signals with the second systems. So they are the same. So this slide basically is what I have explained earlier. When you have a signal convolute with a systems is equivalent to the other way, where a system convolute with a signal. For associative law, when you have a signal that need to passes through two systems, it is equivalent to a signal that pass through a single system, where this system is the convolutions of both systems together. Finally, distributive law, it says that if you have signals that pass through two different systems, in this case two different systems, and then you sum up the outputs of these two different systems, is equivalent to a signal that pass through the summations of the two different system itself. So it is kind of like to simplify your block diagrams or to simplify your mathematics when you do convolution. And this is the summary of what you have learned today. First, you learn about discrete time convolutions, where you have three methods. One is a mathematical method where you apply directly the formula. Two is a graphical method where you reflect one of the signals and then you slide it to the right, and then you find out what is the superimposed multiplications and additions of them. And then the third one is to draw a tables, and then you just multiply both the element together and to find out what is the final answer. And I would personally prefer method number 3 for discrete time convolution. And then we move on to continuous time convolutions, where you cannot use method 3 anymore, but you can still use method 1 and 2. But for the graphical method, you can only use it if both the graph are square wave. Then only you can be able to find out the area, and area multiplied by the magnitude. And lastly, we learn about properties of convolutions. There are 3 of them, which is the commutative properties, the associative property, and the distributive property. So coming up next in the next week lecture, you will learn on Fourier series. So I will see you again next week.